the square root of negative 4. Now you might think, oh, that's an illegal operation, right? This is going to be undefined. Well, in fact, it will not be undefined if you consider the set of complex numbers. Now, we treat this unit, negative square root of negative 1. This is called, we call it I. It's the imaginary unit. This also means that I squared is equal to negative 1. And so what we can do with this is basically factor out the real portion. So you're going to have the square root of 4 times the square root of negative 1. So then you're going to be left with 2i. Complex numbers are when you combine imaginary numbers and real numbers in a type of sum where it's basically z is equal to a plus bi. And so this is the real part and this is the imaginary part. If we want to consider real numbers and counting in terms of the number line, we're basically going to have it like this. Put 0 here. I'm just going to use integers for simplicity. And then the negatives. Say we want to add 1 plus 2. And if we could basically treat these like vectors where we have 1 and then plus 2. The overall movement is the same as going 3 units all the way this way. So you have 1 plus 2 is equal to 3 basically. But if we want to consider complex numbers, where would they go on the real number line? Well, they can't go there. There's no place to put them. So then how about this? How about we stick it vertically? So it's going to be a complex plane like this. And so now let's just put everything in here. We have 1, 2, 3, negative 1, negative 2, negative 3, and then here we have I, 2i, and 3i. And then same here for the negatives. We have negative I, negative 2i, and negative 3i. Let's say we want to write or plot the complex number 2 plus I. Well, we're going to go, let me change the color. We're going to go 2 units right on the real axis and then 1 unit up on the imaginary axis. So then basically here at this point, this is the complex number z equals 2 plus I. So yeah, you treat it as the real axis and then this is the imaginary axis. Now let's look at powers of I. Okay. So we know I to the 0, anything to the 0, that's just equal to 1. I'm going to write this as the square root version. But yeah, so this is just equal to 1. Then if we have I to the first power, well then that's just equal to the square root of negative 1, which is just I. If we have I to the second power, this is basically square root of negative 1 squared, which is just equal to negative 1. Now, if we look at I to the third power, well, that's just I times I to the second power, right? So then what you're basically going to have is I times negative 1, which is just equal to negative I. Then if we have I to the fourth power, then this is just I times I to the third power. So this is going to be I times negative I, which is equal to negative I squared which, so this is just negative times negative 1, which is just equal to 1. And if you actually continue this, you're going to keep noticing that as you increase the powers of I, it's going to keep following this periodic motion. 1, I, negative 1, negative I, and then 1 again. It keeps going. And so if we want to represent this on the complex plane, it's going to also be a periodic motion around the unit circle. So if here we have 1, I, negative 1, negative I. I'm going to draw this here. The unit circle, this should pass through all the points. So now we're going to have a movement. If you want I to the first power, it seems to be a rotation 90 degrees. Right over here you land on I. I to the second power, another rotation, you're going to land on negative 1. Then if you go another time, this is I to the third power, you're going to land here on negative I. And then I to the fourth power is just back where we started on 1. And so this is just going to keep on going as you increase the powers. It always follows this periodic motion. So now we're going to talk about ways to represent complex numbers. As you saw at the beginning, that way was shown in technically rectangular form. I'm going to use x and y now, where you basically treat the real part as your x-coordinate and then the imaginary part as your y-coordinate. And so if you want to represent this in the complex plane, we saw before, it's the imaginary, this is the real, and so I'm just going to let this be x, and then this is going to be iy. So you're going to move x units horizontally and then y units vertically. And the overall effect, so you can basically represent this as vectors x plus y, kind of like that. Now there is also another form which you may have also seen for things like conic sections, but it is way more useful for complex numbers in the complex plane, where you would have a polar form, as it's called, from rectangular coordinates to polar coordinates. And so this, you would basically, instead, you would have a radius and an angle, or in coordinates r theta, like that. So let's draw the complex number plane. We're going to have it like this. And so we're going to consider this from a trig perspective. Okay. So this is still going to be our x and then our iy. And now we are basically going to make ourselves a wedge here. Okay, so you're going to have this radius r and then this angle theta. And so you basically end over here. Now let's consider where how we can model this basically. So considering this, taking it from rectangular form, if we want the radius here, this is almost this is basically like a right triangle. So if you want the radius, well, you know that x squared plus y squared is equal to the radius squared, and that means that the radius is equal to the square root of x squared plus y squared. Now if we want the angle here, we've got this, and we are basically given the x and y coordinates. And if we want the angle, since this is opposite and this is adjacent, what this is going to be is the inverse tangent of y over x. Now how about representing these in terms of a sum of complex numbers like this before? Here it's going to be basically the same way now in terms of trigonometric functions. So what we're going to have, this is by, when you think about this as the unit circle definition, just multiplied by r. When you have x, this is the horizontal component. This is going to be cosine theta multiplied by r. And then with y, it's going to be sine theta, but then you also include the I here. And so we can write it as a sum where you have x plus iy. This is equal to r times cosine theta plus I sine of theta. And so this representation of complex numbers in polar form is very useful, and we're going to see soon when I show you the relation to Euler's formula and Euler's identity. And so as we do this, let's shift our focus to e to the x, the general exponential function of base e. We know that e is equal to 2.718281828, and so on. If we take a look at its Maclaurin series, that's the Taylor series centered at 0, this is going to be the sum n equals 0 to infinity. This was simplified from the original kind of derivative notation, but it would basically be x to the n over n factorial. And so yeah, this is going to expand to 1 plus x plus x plus x squared over 2 plus x cubed over 6 plus x to the 4 over 24, and so on. If we plug in an imaginary number here, say we have, so e to the I theta, since this is how it appears in Euler's formula, then so we're going to get 1 plus I theta plus I theta squared over 2 plus I theta cubed over 6 plus I theta to the 4th power over 24. And I'm also going to add this 5th term now. We're going to see why this is important. We're going to expand this a little bit further. We're going to have 1 plus I theta plus, or well, I squared, that's negative 1. So we're going to have negative theta squared over 2. And then I cubed, that's negative I theta cubed over 6. I to the 4, that's just 1, so we're just going to have theta to the 4th power over 24. I to the 5th, this is just going to be I again, so we're going to have I theta to the 5th power over 125. Now we're going to separate it into its real and imaginary parts, like a normal complex number, a plus bi. So we're going to see over here, this is real, this is real, this is real, and then these guys over here, complex, complex, or well, imaginary. So we're going to have 1 minus theta squared. I'm going to add those back. Theta squared over 2. And then plus theta to the 4th power over 24. And if you added more terms, it's just going to basically be more of the even powers again. So we're just going to close this off. Plus I, because I'm going to factor this out here, I times, I'm going to have theta minus theta cubed over 6 plus theta to the 5th over 125. And again, as you add more terms, this is going to be odd powers and odd factorials. And so you might have noticed this, might have not, but I'll give you a little hint. If you've seen this here, this is actually the Taylor series, or sorry, the Maclaurin series for cosine over here. And then this is the Maclaurin series for sine. So from this, we're going to get exactly that. We're going to get cosine of theta plus I sine of theta. So we can represent the polar form of complex numbers exponentially as well. And so from this, there also comes Euler's identity, where we basically have, e to the I pi. Well, this is just going to be cosine of pi plus I sine of pi. Cosine of pi, that is just -1. Sine of pi, that's 0. So we're basically going to have plus 0i. But we can cancel that out. So we're going to have this. So e to the I pi is equal to -1. Move this to the other side. We're going to have e to the I pi plus 1 is equal to 0. Just like Euler's identity as he showed it before. If we want to consider this on the graph, there's actually a nice way to think about the series over here, the Taylor series. We're going to have the complex plane here, and then I'm also going to draw the unit circle again. So just connect that there. So now if we look again at the Taylor expansion of e to the I pi, so we're going to have 1 plus I pi, I squared, that's -1, so you're going to have negative pi squared over 2, and then I cubed, this is negative I pi cubed over 6, I to the 4th, that's just 1, so we're just going to have pi to the 4 over 24, and so on. And so if we treat these as vectors, what we're going to see is that, so this is a movement 1 in the right direction. Here this is going to be pi movements up. Then you're going to have pi squared over 2 movements left. Then this term, you're going to have pi cubed over 6 movements down. And then, once again, this is pi to the 4th over 24 movements right. And so this is basically going to keep on being a never-ending loop, or well, it's going to eventually converge, as you might expect, on -1. And the way that it moves is that you're going to start here, 1 plus I pi, whatever that is, over here. And then you're going to move to the left, whatever negative pi squared over 2 units is. Then you're going to move down pi cubed over 6 units. Sorry, there we go. Pi cubed over 6 units, whatever that is here. And then you're going to move right again. Right again, pi to the 4th power, 24 units. And you're going to see that this is going to eventually keep spiraling in until it reaches exactly -1. So that's the geometric interpretation on how these kind of powers work with exponential to an imaginary power. So yeah, from this, again, we can take that e to the I pi is equal to -1, which then means that e to the I pi plus 1 is equal to 0. So this was just a nice introduction to complex numbers, their representations in the complex plane, polar form and rectangular form, and then the connection to Euler's formula for the polar form of complex numbers, and the specific case of Euler's identity where your angle is pi, and this is going to converge towards -1. I hope you enjoyed this video. Click like and subscribe. Next video, I'll probably cover de Moivre's theorem, which is all about powers of complex numbers in polar form, a nice little formula to do it simply. So that'll probably be the next video. Thanks for watching, and I'll see you later.